Hello and welcome to Lesson 5 in the GPS course. This lesson will be about geodetic datums, and the reason is because it is not possible to use a GPS without engaging in geodesy. In other words, deriving coordinates that take into account the fact that the Earth isn't flat, is a simple way to put it. And so it is necessary to understand what the native format of GPS coordinates is, and how those elements of geodesy that influence those coordinates operate. Once there's an understanding of these aspects of geodesy, and of course there's just certain aspects of geodesy that we're going to discuss, not the entire subject by any means, then it's better it's better that way to understand the coordinates that you will derive from your work and apply them correctly. Geodesy is a complicated subject, but as I say, we will be talking about just a few elements of the science. This slide shows a construction of a three-dimensional Cartesian coordinate system, and we'll discuss this more as we go along. But it's a right-handed system in the sense that extending the forefinger of your right hand is the x-axis. The middle finger of the same hand extended at right angles symbolizes the direction of the y-axis, and then the extended thumb pointing up is the direction of the pole, the North Pole in this case, right-handed in that sense. And as you see, the relationship, of course, rectilinear, 90 degrees from each other, and it is possible to express a point on the Earth's surface in terms of these x, y, and z coordinates in what is known as an Earth-centered, Earth-fixed, or ECEF system. And as I say, we'll discuss this even more, but the reason to start here is because, as you will discover, this is the native system. This is the fundamental system of every GPS coordinate that is derived on the Earth's surface. Now, obviously, the plane of the equator, the mean equatorial plane, and the zero meridian, or the prime meridian, are vital to this system. And the prime meridian corresponds, as you see, with the x-axis, and the y-axis then is perpendicular to that at 90 degrees longitude east and west, and then the polar axis is the z-axis, which is known as the International Reference Pole. These three axes can be used to describe terrestrial positions based on space geodesy, in other words, based upon satellites that orbit the Earth. This arrangement is known as the Conventional Terrestrial Reference System, or CTRS, and the Conventional Terrestrial System, or CTS, is the name that I will be using. Now, the origin of the system, of this three-dimensional Cartesian coordinate system, is the center of mass of the Earth, or the geocenter. Another way to describe this is that it is geocentric. The mean equatorial plane and the zero meridian, of course, we've discussed. But this system, again, is a way to define a position on the Earth's surface, or for that matter, position above the Earth's surface. In other words, it would be possible, it is possible, to have an XYZ coordinate in this system of an orbiting satellite. Again, because the satellites themselves orbit around the center of mass of the Earth, it is obviously sensible to have the coordinate system derived from satellites with its origin at the center of mass. Now, it becomes obvious immediately that this abstract idea of a three-dimensional coordinate system is perfect in its theoretical sense, but when you attach it to the actual physical Earth, difficulties obviously arise. For example, as pointed out here in this slide, the Earth's rotational axis just won't hold still. The Earth wobbles, if you would like to call it that. There's actually two components to this wobbling, this oscillation. The largest, as it says here, is the 430-day cycle known as the Chandler period. And the actual displacement caused by this does not exceed about 12 meters. But obviously, if one were to say that the z-axis of the system depends on the actual polar axis of the Earth, it would wander along with this this period. That, of course, wouldn't be workable. So, the mean position of the rotational pole has been chosen. It has been, since 1989, been defined by the International Earth Rotation Surface, the IERS. Now, we'll be talking some more about this organization. It does some very useful things in terms of GPS. But in any case, the z-axis has been geometrically stable with a clear definition as regards WGS-84, the World Geodetic System of 1984. So by international agreement, the conventional terrestrial system has a line which is called the CTP, or conventional terrestrial pole. Now, the point of this whole discussion is that the z-axis of this Earth-centered, Earth-fixed three-dimensional Cartesian system is fixed by international agreement. And you can see it there indicated by the CIO dot, which is right there on the x-axis. And this is a averaged position between 1900 and 1905, and that's the position that is set and agreed upon to be the z-axis of the three-dimensional Cartesian coordinate system we're discussing. In this slide, you see a page of printout from a processing that was done some time ago in 1993. But the point of the sheet is simply the dx, dy, and dz numbers. These numbers are the difference in x, the difference in y, and the difference in z in this three-dimensional Cartesian system. Now, these differences are the differences between the xyz coordinate of one end of a baseline and the xyz coordinate of the other. So in other words, it's possible to define the vector by the difference in x, the difference in y, and the difference in z in this three-dimensional Cartesian coordinate system based on the center of mass of the Earth. And this is the way that the GPS receivers actually define the coordinates that are derived. So from these coordinates, it is possible, of course, to derive any number of others, to derive plane coordinates in the universal transverse Mercator system, or in the state plane coordinate system, or in latitude and longitude. But they are derived from the XYZ coordinates that are in the three-dimensional Cartesian Earth-centered, Earth-fixed system. Okay, let's step back a moment then and talk about perhaps more familiar coordinate systems. Latitude and longitude is fairly familiar to most. And here, of course, are some straightforward illustrations of those coordinates. longitude on the left with the prime meridian through Greenwich, or approximately through Greenwich. And then, of course, west longitude, which is negative, is in our neck of the woods, and then east longitude going the other way around, meeting at the 180-degree longitudinal value. Longitude is usually symbolized by lambda, Greek letter. And then on the right, the latitude, of course, measured from the equator, north and south, north being positive, south negative. And these planes in this picture tended to indicate 45 north latitude. This is undoubtedly more common than the XYZ Cartesian system that we were just discussing. But one point I want to make right away is that when one talks about latitude and longitude, there is more than one kind, more than one flavor, depending upon the datum on which you're discussing them. So far we've been discussing WGS 84, which is the native datum of GPS, and that is one type of latitude and longitude. Another would be based upon GRS 80, which is the datum of NAD 83, the North American datum 1983, which is used, as it says, in North America. That latitude and longitude is not the same as the latitude and longitude of the WGS 84, because the datum itself is different. And we'll talk some more about that. And to begin that discussion of geodetic datums, we'll talk about the idea of down, the deflection of the vertical. But one of the things I want to point out about this image that we're seeing here, this slide, is notice the astronomic coordinates of a station. This is an actual station called Youghal in North America. The astronomic coordinates of that station, 40 degrees, 25 minutes, 36.28 seconds, differ from the geodetic coordinate, the latitude in that case being 4025, 33.39, and the longitude in astronomic, 108 degrees, 46 minutes, 0.08 seconds, and the longitude in geodetic coordinate, 108 degrees, 45 minutes, 57.78. Now, the reason that these differ to such a large degree is because when one does an astronomic observation, down is according to gravity. However, when one does geodetic calculation of latitude and longitude, down is perpendicular to the ellipsoid that one is using. And of course, an ellipsoid is something that we're going to have to discuss some, but in shorthand terms, it is a smooth, mathematically determined representation of the Earth. It isn't plagued with the irregularities of the actual terrestrial surface, nor the irregularities of gravity. It's a smooth, ellipsoidal surface that is used to approximate the surface of the Earth. As I say here, how can latitude and longitude be considered inadequate in any way to define a position on the Earth? The answer relies on the fact that there are several categories or types or flavors of latitude and longitude. From the various options, astronomic, geocentric, and geodetic, the discussion here will concern geodetic latitude and longitude as they are typical. Its definition has a good deal to do with where down is. And down, this deflection of the vertical really is the difference between the direction of gravity, as you see, and perpendicular to this representation of the Earth, perpendicular to the ellipsoid. Those are two different directions at a particular station. And those influence the latitude and longitude. The point that I am trying to make primarily is that one should not think that latitude and longitude coordinates are independent of the datum or independent of the ellipsoid that you are discussing. They are very dependent on the datum. Down seems like a pretty straightforward idea. A hanging plumb bob certainly points down. The string follows the direction of gravity. But as you see on this image here, in the upper part we have an instrument that's set up on the Earth's surface, topographic surface, and the red dashed line is perpendicular to the ellipsoid at its point, at the point where we find the instrument. The black line is the direction of down according to a plumb line or according to gravity, and the deflection of the vertical is the difference between them. Now in the lower part of the image you see the down according to the direction of gravity is the again, according to the direction of gravity is the red dashed line, and a geodetic latitude is based upon down according to perpendicular to the ellipsoid. Now in the lower image it is the blue line, the one that is perpendicular to the ellipsoid, that is the line that we normally use to define latitude, the one that is perpendicular to this ellipsoid. This is normally called geodetic latitude. And then of course there's a third kind, and this is the geocentric latitude, and this is the one that goes from the point on the Earth's surface to the geocenter, or the center of mass of the Earth. So the one that is of interest, and the one that is used most often, is the geodetic latitude, which is based on perpendicular to the ellipsoid. The reason that this issue in coordinates has arisen is because before GPS was a primary system, before GPS even existed, determination of latitude and longitude was done primarily with astronomic observations. And these astronomic observations, of course, were done with optical instruments that were set up on the surface of the Earth and used the direction of gravity to center over the stations from which the observations were made. Because of that, the latitudes and longitudes that were derived were, of course, astronomic latitudes and longitudes. Now, in the past, the National Geodetic Survey corrected those coordinates and made them geodetic, as you see here. And this is one of the reasons we're used to using geodetic latitude and longitude. Now, geocentric comes into the picture because, as we've discussed, the satellites that orbit the planet orbit around the center of mass of the Earth. So therefore, again, to convert those geocentric coordinates to geodetic requires a certain amount of conversion. Now this ellipsoid that we're perpendicular to with a geodetic latitude, again, is a figure that is mathematical, that is based upon a semi-major and semi-minor axis. It's smooth and regular and consistent. And the one that we use when we're talking about GPS is WGS84. That's its native datum. I see now that this slide is a duplicate of the previous slide. So we'll proceed beyond this. Now obviously the difference between these directions of down can be extended upward, and the deflection of the vertical is indicated on the upper image between the two lines, the direction of gravity and the perpendicular to the ellipsoid. It's interesting that an optical instrument set up over a point on the Earth can't really measure geodetic latitude directly, because the latitude and longitude that is measured in geodetic latitude is based upon this ellipsoidal model of the Earth. Gravity doesn't come into it. On the model of the Earth, down is the line perpendicular to the ellipsoidal surface at a particular point. On the real Earth, down is the direction of gravity at the point. And they're not the same thing. Usually the difference is very small. But since the ellipsoidal model of the Earth's imaginary, you can't set up an instrument on it. On the other hand, the old measurement of latitude and longitude by astronomic observation is a very long history. It goes back literally centuries. So conversion from astronomic latitude and longitude to geodetic latitude and longitude has a long history too. But until the advent of GPS, almost always were latitudes and longitudes derived from astronomic observations and calculations after the fact. And as I say, it really is essentially still the case, because a GPS receiver can display geodetic latitude and longitude of a point almost immediately because of the fact that a GPS receiver has an onboard computer and can do that conversion virtually instantaneously. But the fundamental fact is that instruments by which latitude and longitude are measured are oriented to gravity, and the ellipsoidal model isn't. And that's just as true for an antenna of a GPS receiver as it is for an optical surveying instrument, a camera in an airplane, or anything else. So the whole point really of these few slides has been to illustrate that latitude and longitude are dependent upon the datum on which they are measured. That is really the fundamental and most important point to carry away. The secondary point is that when we speak of latitude and longitude, we almost always mean geodetic latitude and longitude based upon an ellipsoidal model of the Earth. Now let's talk about that model of the Earth. The second part of the answer to how can latitude and longitude be considered inadequate to define a position on the Earth is, as I've said, they must have a datum. And despite the fact that the Earth itself is obvious and a physical fact, we are used to our legacy of displaying that surface on a flat map. And we have a whole long list of map projections that have been used to accomplish this conversion of what is obviously a curved surface onto flat maps. But any of these projections, no matter how complicated they might be, cannot do so without distortion. And so therefore, really, the technologies we deal with in terms of building those kinds of flat maps or plane coordinate systems are an exercise in trying to minimize that distortion. The distortion itself is inevitable, but we always try to minimize the distortion. Well, the first step in doing that has always been the building of a model of the Earth. And for a good long history, we have been trying to grasp that nature of the planet's size and shape. Ever since 200 BC, Eratosthenes almost got the planet's circumference right, and of course the fundamental idea that it was in fact a sphere, or nearly a sphere. What he did was interesting. At noon, the midsummer sun was visible in the water at the bottom of a deep well in Siena. The sun was obviously directly overhead, and on the same day, the measurement of the noon shadow cast at the pillar at Alexandria showed that the sun struck the earth at an angle of 7.2 degrees from vertical. So therefore, the angle between Alexandria and Siena had to be 7.2 degrees, or 1/50th of 360 degrees, a circle. And therefore, since it was measured by the rope stretchers that Siena was 480 miles south of Alexandria, and a great circle must therefore be 50 times 480 miles, or 24,000 miles, for the circumference of the entire planet. Extraordinary deduction for 200 BC, and not so terribly far from the truth. Now, since that time, of course, up until today, there have, as I say, been periods of unmitigated nonsense on the subject, but Eratosthenes was close to right. Another leap forward occurred when Newton's thesis that the Earth was an ellipsoid rather than a sphere came in the first edition of his Principia in 1687. Newton had a colleague in J. Richter, and one of the observations that I account here is that Mr. Richter had a 1-second clock that he used in his observations in French Guiana. And he found that in order to keep his clock regulated, he had to shorten its pendulum significantly because it swung more slowly as he approached the equator. Newton said that the reason that it swung more slowly was the fact that the force of gravity itself was lessening as one approached the equator. And he explained this idea by saying that the Earth is higher. In other words, the Earth is further from its center of mass at the equator than it is at the poles. And he calculated that it was higher by approximately 17 miles. Obviously, if the Earth is to be more massive at the equator, bulging out at the equator, this means that the Earth is ellipsoidal, and that it is squashed, let's say, at the poles and bulges out at the equator. In other words, it's an oblate spheroid. And this, of course, has turned out to be the case. Geometric verification of the idea of an ellipsoidal Earth was done with arc measurements at different latitudes. If you establish the beginning and ending points with astronomic observations and then measure along a cardinal line, a north line, you can discover the length of a 1 degree of longitude along that arc. Now, early on, the idea was that there was a spherical Earth, and the results were used to estimate the radius. One of the most accurate measurements, as it says here, began in 1669 by J. Picard, was used by Newton in formulating his own gravitation law. However, Cassini looked at the arc measurements, and it seemed to indicate that the length of 1 degree of longitude actually decreased as it proceeded northward, and this would mean that the Earth wasn't flattened at the poles, but elongated at the poles. So there were many expeditions, and the ones that really resolved the issue were the groups the French sent to the Arctic, 66 degrees north latitude in Lapland, and another that was done near Ecuador, what is now Ecuador, 1 degree and 31 minutes south latitude. And these measurements proved Newton correct, that the earlier measurements were somewhat in error, and in fact the Earth is flattened at the poles, or is an oblate ellipsoid. And here we have the modern setup of determining an ellipsoidal model of the Earth. The semi-major axis, you see there in blue, half of the major axis of an ellipse, can be given a value, and then the semi-minor axis, half of the minor axis of the ellipse, can be given a value. And then using the north-south axis of revolution and rotating this ellipse around into a solid, it becomes a biaxial ellipsoid, bulging at the equator, flattened at the poles, and this oblate version has been used ever since as a way of defining an Earth model. Now, flattening, which you will hear frequently, is a little formula here. The semi-major axis minus the semi-minor axis divided by the semi-major axis is a value that's called flattening. But clearly, one can define an ellipsoidal model fairly easily with a semi-major and a semi-minor axis, and then a flattening value. Of course, the next question, once an ellipsoidal model is established at the correct size, or close to the correct size for the planet, is how do you attach it to the Earth? What's the origin? Now, the semi-major and flattening can be used to completely define an ellipsoid of revolution. That's an ellipsoid revolved around its minor axis, that north-south axis. But you need 6 additional elements if that ellipsoid is to be used as a geodetic datum. 3 to specify its center, 3 more to indicate its orientation at that center. Now, the Clark 1866 spheroid, which is an ellipsoid, was one of many reference ellipsoids, and its shape was completely defined by a semi-major axis, 6378.2064 kilometers, and a flattening, F, 1 divided by 294.9786982. And it was the reference ellipsoid of the datum known as North American Datum of 1927, or NAD 27. Now note that the ellipsoid, the Clark 1866 ellipsoid with those values, was the reference but not the datum itself. For that ellipsoid or that spheroid to become a datum, it had to be attached to the Earth at a point and specifically oriented to the actual surface. And this ellipsoid, which fits North America very well, of course it doesn't conform to the surface of the Earth perfectly, but an initial point was chosen near the center of this geodetic network, and that was at Meade's Ranch in Kansas, at the latitude and longitude given there. The geoidal height, we'll talk about what that is exactly later, but the geoidal height was presumed to be 0, and it was attached at that point. But those coordinates weren't sufficient. You had to then orient that Clark 1866 ellipsoid around that initial point. And so therefore an azimuth was established from Meade's Ranch to Waldo, which is a station, and fixed as 75 degrees, 28 minutes, and 09.64 seconds. And the deflection of the vertical was set to 0. Once the initial point is fixed on a datum, such as NAD 27, the idea always was that the center of the ellipsoid was somewhere near the center of mass of the Earth, but there was no requirement that it be so. It wasn't intended to be a geocentric ellipsoid. The fact that the North American datum 1927, using the Clark 1866 ellipsoid, also known as a spheroid, the fact that this surface matched well with North America was enough. Whether or not it was geocentric was of little or no concern. This was, of course, before space-based geodesy was possible. The world was, and is still, populated with numerous regional datums. The Australian Geodetic Datum 1966, European Datum 1950, South American Datum 1969, and many, many others. They're not geocentric, weren't intended to be geocentric. Actually, in modern times, it's become clear that NAD 27 is in X, Y, and Z about -4 meters, Y plus 166 meters, and Z plus 183 meters from the actual geocenter, approximately. The idea that a datum is geocentric was of no concern, really, or little concern, when the measurements upon which it was based were optical, were terrestrial, were done on the surface of the Earth. And even after the advent of electronic distance measuring, the general approach involved the determination of horizontal coordinates by measuring from point to point on the Earth, and then adding heights, otherwise known as elevations, through a separate spirit leveling process. And for this whole time, there was this separation between the idea of horizontal and vertical coordinates that to some extent still continues. Obviously, the Earth-centered, Earth-fixed XYZ coordinates don't have such a separation. Now, this idea of geocentric datum, though, became very important with the advent of satellites and satellite geodesy. For there to be full advantage of the capabilities of such a high platform, obviously a system had to be developed that was truly global, and horizontal and vertical not really separate. And since satellites orbit around the center of mass of the Earth, a position based in space-based geodesy, as can be visualized as a vector originating from that point. So the horizontal and vertical components are part of that same vector. And the position vector can be transformed into 3D Earth-centered, Earth-fixed XYZ or CTS position. The traditional latitude, longitude, and height, or virtually any other well-defined coordinate system. However, since the orbital motion and subsequent position vector are derived from satellite geodesy themselves, are Earth-centered. The satellites, in other words, orbit around the center of mass of the Earth. Therefore, the most straightforward representation of that data should be Earth-centered as well. And that, of course, is where we began the current discussion. Cartesian XYZ coordinates, Earth-centered. Now, in this representation on this slide, we see really the same image as was on the first of this presentation. There's a point on the Earth's surface. XYZ coordinates are indicated from the center of mass of the Earth in a three-dimensional Cartesian system. However, there's some additions. One thing you see is the longitude, symbolized by lambda, from the prime meridian over to a point on the equatorial plane, and then from there, latitude up to the position of this point as represented on the ellipsoid, the reference ellipsoid of the datum. And the original picture The original slide had no ellipse on it, no ellipsoid. It was simply the XYZ coordinates, and this is an important distinction. If we're going to have a latitude and longitude derived from an X, Y, and Z, we have to specify which ellipsoid, which datum, and of course the datum is attached to the Earth, a datum that we're operating in. If we say WGS 84, then we get one latitude and longitude. If we say GRS 80, we get another latitude and longitude. So, we have to have an ellipsoid to derive a latitude and longitude. Change the shape of the ellipsoid, the latitude and longitude change. Now the position vector you see in red from the center of mass up to the point. However, we see a different vector that's perpendicular to the ellipsoid. It doesn't go to the center of mass. This is the transformation we talked about. And then finally, notice that if we're going to go from the position on the ellipsoid up to the actual surface of the Earth, we add a height, an ellipsoidal height. So, we can identify this position on the Earth's surface by an Earth-centered, Earth-fixed XYZ coordinate, or we can identify the same point with a geodetic latitude and longitude and height. These are just different coordinate systems for expressing the same point, the position of the same point. However, change the datum and the coordinate changes. Now, while the satellites that we use today, GPS satellites, allow us to do positioning of the type we're discussing, they've also contributed a great deal to our understanding of the shape of the Earth. The changes in the orbits of satellites ever since Sputnik and Vanguard have given us more information about the details of this oblate ellipsoid that our planet is. These deviations in the orbits are caused by the action of the Earth's gravity, primarily, on the satellites. There are other elements, too. But just like Richter's clock reacted to lessening gravity at the equator and revealed some of the larger features of the Earth's shape to Newton, small perturbations in the orbits of the satellites responding to gravity reveal the details of the Earth's shape today. They allow us, along with other sensors, to be able to determine the direction and magnitude of the gravity around the planet. And of course, the direction and magnitude of gravity changes from place to place because the Earth is not equally dense in all places. And so therefore, gravity varies. And the surface that indicates that variation is known as the geoid. The geoid is sometimes illustrated as the surface of the sea, sometimes known as mean sea level. I hasten to add, however, that mean sea level and the geoid are different. They are not the same. Close, yes. The same, no. One of the major reasons that mean sea level cannot be the same as the geoid is that the actual oceans of the Earth are affected by temperature, by wave motion, by salinity, and many other aspects that cause variation in their heights. So even with tidal monitoring, mean sea level is not an indicator of gravity alone, and that is the concept of the geoid. The geoid is that surface which is affected only by gravity. It is an equipotential surface where the gravity potential is always the same. Now, the oceans of the Earth can be thought of as an approximation of that idea. And if there was only gravity acting on them, and these waters were entirely calm, then of course the geoid and sea level would be exactly the same. But of course the physical oceans are not nearly that cooperative. Still, it's a useful imagination of the geoid, to think of it as what the oceans would do if they were affected only by gravity. As I said, the geoid is an equipotential surface, and as we see on this image of what a lumpy surface our Earth would be if we only considered gravity. Of course, this is exaggerated, but you can see that gravity isn't consistent across the entire topographic surface of the Earth. Everywhere it has a direction and a magnitude. In other words, anywhere on the Earth, gravity can be described as a vector. And such vectors don't have all the same direction and magnitude, but you can imagine a surface that does have a constant gravity potential. And this would be the level surface in the truest sense. For example, when you think of an instrument being set up on the Earth, like a GPS receiver, and it is leveled, it is of course leveled in relation to gravity, in relation to this surface that we're talking about. This would coincide with the top of this hypothetical water of mean sea level. So, the vertical axis of any properly leveled surveying instrument and the string of any stable plumb bob are perpendicular to the geoid, just as the pendulum clocks and the Earth-orbiting satellites. They clearly show that the geoid is a reality. It is a physical reality. Now I hasten to add, remember, that the ellipsoid, the nice, smooth, mathematical surface that we use as a reference in Datums, is different than the geoid. They are two different surfaces. One is gravity, the geoid, and the other is a purely mathematical imaginary surface, and that's the ellipsoid. And here we have an image of three figures, and one is the topographic surface of the Earth that we walk around on, and the next in the red dashed line is the ellipsoid, and the third in the blue wavy line is the geoid. Now, the geoid doesn't follow mean sea level, doesn't correspond with the topographic surface. It's irregular. It does have peaks and valleys. It's bumpy, in other words, and of course because of the uneven mass of the planet. If the solid Earth didn't have these changes in density, the geoid and the ellipsoid would be the same thing. But of course, gravity isn't nearly so cooperative. The geoid actually departs from the ellipsoid up to 100 meters in some places. So, the figures involved in a geodetic datum, let's say for latitude and longitude and height, are the geoid, the reference ellipsoid, and the Earth itself. Because of satellite geodesy, we've been endeavoring to make all of these share a common center. Well, the topographic surface, of course, shares a center of mass. That's obvious. And what we want to do is be able to have the ellipsoid, that's the reference ellipsoid we use for satellite geodesy, to be Earth-centric or geocentric. Now, while the level surface of the geoid provides a solid foundation for the definition of heights, and the topographic surface is necessarily where the measurements are made, neither can serve as a reference for geodetic positions. From the continents to the floors of the ocean, the solid Earth is too irregular to be represented by a simple mathematical statement, and the geoid, sometimes under, sometimes above the surface of the Earth, has an overall shape that also defies any concise geometrical definition. But the ellipsoid not only has the same general shape as the Earth, but unlike the other two figures, can be described simply and completely in mathematical terms, and that's why we use the ellipsoid as a reference. Therefore, a global geocentric system has been developed based on the ellipsoid adopted by the International Union of Geodesy and Geophysics. It's called the Geodetic Reference System, GRS 80. And here are the semi-major and semi-minor axis and its flattening. Notice that it's 1 part in 298.25722 in the flattening. However, GRS 80 is not the reference ellipsoid for the GPS system. That is the WGS 84 ellipsoid. And here you have a comparison between the two, and you will notice that the semi-major axis is the same, and the inverse flattening is only different when you get out to the 6th place to the right of the decimal. Very, very similar to the same ellipsoid. The WGS 84 ellipsoid is the foundation of the coordinate system known as WGS 84, and this datum has been used by the U.S. military since January of 1987 as the foundation of GPS. Now that we've discussed what a datum is, I believe you have a good concept of what this means. In other words, the WGS 84 ellipsoid, used as a reference, attached to the Earth, at the center of mass of the Earth, is the ellipsoid used by the Department of Defense in, for example, the navigation message that we receive from the satellites. But while WGS 84 has been the basis of GPS navigation, as of this writing, the latest version of WGS 84 is called WGS 84, notice in parentheses, G1150. This refers to the 1150th GPS week, counting from the beginning of the system. This is the latest update of the WGS 84 datum. It's worth noting that the number following the G is the number of the GPS week. Therefore, coordinates provided today by a GPS receiver are based on WGS 84 G1150, which is the same thing as the International Terrestrial Reference Frame 2000, or ITRF00. We'll talk more about that later. However, most available GPS software can transform those coordinates to any number of other datums. So in other words, while the navigation message and the coordinates from the GPS receiver in Earth-centered, Earth-fixed XYZ are in WGS 84 G1150, these can be transformed into, for example, North American Datum 1983 or NAD83 coordinates, which of course are different. Originally, the difference between WGS 84, as originally rolled out in 1987, and NAD83, as first introduced in 1986, was so small that transformation was unnecessary, but that is no longer the case. And this is an important point. NAD83 cores 96 coordinates, and WGS 84 G1150, these are the latest incarnations of these coordinate systems, can differ to up to 1 to 2 meters. They are not the same. This is an important distinction. Now, it is not that they are always 1 to 2 meters different, but they can be up to 1 to 2 meters different. Now, this is the third update on the WGS 84 reference frame. The first was WGS 84 G730, and then there was WGS 84 G873, and the latest is WGS 84 G1150, which was implemented by the GPS Operational Control Segment January 20th, 2002. Now, NAD27, or the North American Datum 1927, is not entirely outmoded, but is getting there. Of course, these positions were not derived from satellite geodesy. They were produced from optical observations in chains of triangulation that was done across the United States for many, many years. The work was excellent, and given the technology of the day, remarkable. But of course, based upon this coordinate system, this datum, NAD 27, brass tablets were placed all over the United States that are still reference marks that are used today. But originally they were established optically. Even though the work that was done was excellent, judged by newer standards, like eventually satellite geodesy, the system wasn't viable and originally useful, but gradually became more and more untenable for future use given new technologies. So by the early 1970s, the NAD 27 coordinates of the National Geodetic Control Network were no longer adequate. NAD 83, or the North American datum 1983, the work on this was begun in 1974 for all practical purposes. The United States Coast and Geodetic Survey eventually became the National Geodetic Survey, NGS, which carried on the work to the production of NAD 83. Now this datum not only includes the United States, but Central America, Canada, Greenland, and Mexico. And the Geodetic Survey of Canada also set about attaching and orienting to the GRS-80 ellipsoid. It took more than 10 years to readjust and redefine all the horizontal coordinates into what is now NAD 83. It's interesting to note that while the modern technology of the day was used in this substantial work, EDM measurements, astronomic azimuths, Doppler stations using the old transit system, and even some very long baseline interferometry vectors, GPS actually only contributed 5 points to the original incarnation of NAD 83. That situation, of course, changed as time went on. Now, a little bit about the International Terrestrial Reference System. These vectors that you see on this slide indicate the motion of the tectonic plates. You can see the legend there, the length of 1 centimeter per year. And this shows you the directions that these tectonic plates are in motion relative to the center of mass of the Earth. As NAD 83 has aged, there have been a constant improvement in geodesy. When NAD 83 was created, it was intended to be geocentric, but now we know that it's about 2 meters from the true geocenter. And other difficulties arose. The geocentric realization of the International Terrestrial Reference System, and the best reference frame currently available, which is the International Terrestrial Reference Frame, or ITRF, has its origin at the center of mass, and the unit of length is a meter, and the orientation of its axis was established as consistent with the International Earth Rotation System. Remember them? The IERS, and their predecessor, BIH. Today, the ITRF is maintained by the IERS, which monitors the Earth orientation parameters for the scientific community through a global network of observing stations, done with GPS, very long baseline interferometry, lunar laser ranging, satellite laser ranging, Doppler orbitography, and radio positioning, called DORIS. The positions of the observing stations are now considered to be accurate to the centimeter level, recognizing that several hundred control stations worldwide for which it publishes yearly coordinates are actually in motion due to the shifting of approximate 20 tectonic plates. The IERS provides velocities for these control positions. The International Terrestrial Reference Frame is actually a series of realizations. The first was 1988. In other words, it's revised on a regular basis. The idea is that now we are actually looking at a worldwide scale with control positions that are in motion relative to one another on 20 or so tectonic plates. And the IERS periodically updates their realization of this International Terrestrial Reference Frame. Now, the North American Datum, 1983, its latest is the NAD 83 Coors 96. As mentioned earlier, in the not-too-distant past, we didn't have to be concerned with the shifts between NAD 83 and WGS 84 because they were well within our overall error budget. But now, as you know, there is a shift between the two because WGS 84 has been upgraded. Now is virtually identical with the International Terrestrial Reference Frame 2000, and so therefore there's divergence between NAD 83 and WGS 84. Now, fortunately, NGS has a software package called the Horizontal Time Dependent Positioning, or HTDP, in which you can transform a coordinate based on its movement over time. But the important thing to note is that the current ITRF WGS 84 system is global. It is in constant motion due to shifting tectonic plates. However, the current NAD 83 system is fixed to one plate, the North American plate, and moves with it. Consequently, NAD 83 in the continental United States moves approximately 10 to 20 millimeters per year in relation to the ITRF WGS 84 system. Now, presuming that a person is working in North America and in the NAD 83 system, those coordinates, of course, are available in various ways, not the least of which are the brass caps or brass tablets established many years ago. But in addition to that, more useful for GIS sort of applications is the continuously operating reference station network that the National Geodetic Survey has implemented. The original idea was to provide positioning and navigation for marine needs. There were about 50 of them in 1996, and their positional accuracies are 3 centimeters and horizontal, 5 centimeters vertical. But today, there are a whole lot more than that. There's at least 165 stations in the National Coors network. And these stations provide base stations against which one can do differential GPS without having your own dedicated base station. In fact, NGS on their website provide constant available downloads from these Coors stations that you can pull down over the internet and process your GPS work against so that you can derive differential positions. This is a very valuable resource. And now here's some news to end this particular lecture. On March 2002, NGS upgraded NAD 83 positions and velocities for all Coors sites, except those located on Pacific Islands, so that they equal the transformed values of recently computed ITRF 00 positions and velocities. This upgrade will remove inconsistencies among previously published NAD 83 positions and velocities, which are detectable with modern high-accuracy GPS. And here is an example directly from the internet on a station in Nevada. Now notice some things here. First of all, you see the ITRF position, 00 position, X, Y, and Z. And you know now, based on this lecture, what that indicates. And here you see it transformed into a latitude, a longitude, and an ellipsoidal height. Also, you see the velocities. And the velocities of the ITRF-00 are shown in meters per year, given in X, Y, and Z, and northward, eastward, and upward. Then next, you see the NAD83 positions in the same X, Y, Z, and latitude, longitude, and ellipsoidal height. Now, this is a very, very good resource. You see how these coordinates are different, the NAD83 positions and the ITRF positions. But let's suppose that you were using the Coors Station Carlton Square in Nevada. You would have the option of post-processing your GPS position based upon either the NAD83 position or the ITRF position. So you could have coordinates in either datum, depending on which you desired. Again, a very, very useful resource. And you see the website there down at the bottom of this slide. Thank you very much for spending this time with me.